जूम क्लाइंट का प्रॉब्लम है सर, वर्जन का प्रॉब्लम लगा था इसलिए बंद कर रहा था।
Yeah. Sir, can we wait for 2 minutes so that more, it's 77 now. We can wait just 2 minutes and then we can start.
Yeah, sure. But before I start, you're going to start, right?
Yeah. I'm taking your permission, sir.
Yeah. Yeah, I'm ready whenever you are.
Okay, sir.
Mr. Sir, good evening. This is Professor Ajay Mandal.
Hello.
Heading the department. So, sir, you are most welcome to this lecture, and I will like to thank you kindly agreed to deliver this lecture. And I just see that you are alumnus of this institute. So it is a quite great event for us. So, did you visit? When did you visit last time, ISM?
I was there, I think, late January, early February 2018.
Okay.
I gave a couple of lectures, one on carbon capture sequestration, one on data analytics. I was there just for 1 day, quick visit.
Okay.
But that was the first time after graduation. So ISM has changed, or IIT ISM now has changed quite a bit.
Yes.
Yeah, most people on this call were probably were not even born when I graduated in 1981.
Yes.
And that was a long time ago.
Right.
Anyway, delighted to be here.
Okay, sure. Thank you, sir.
I think we can start. Okay. Lokesh, Lokesh, you can start now. Yeah.
Yeah, Arslan, go ahead.
Yeah, okay. So, good evening, ladies and gentlemen. My friend Ishika and I, Arslan, on behalf of SPE IIT ISM Students Chapter and the Department of Petroleum Engineering of IIT ISM Dhanbad, welcome you all to a one-day workshop on application of data analytics in petroleum engineering. We also owe the pleasure of having in attendance our esteemed professors from the Department of Petroleum Engineering of IIT ISM. And now for a brief introduction. The utilization of big data analytics is an emerging trend in the oil and gas industry. The recent technological improvements have resulted in daily generation of massive data sets, increasing drilling safety, optimizing performance of production pumps, improving petrochemical assets, and improving occupational safety are among some of the applications of big data in oil and gas industry. This workshop will provide an introduction to statistical modeling and data analytics for petroleum engineering applications. The session will go on for 3 hours from 6 to 9, and we will have 2 breaks at 6:50 and 7:50 of 10 minutes each. Also, if it is not already clear, please keep your mics muted while the session goes on. All queries should go into the chat box, and it is up to the discretion of the speaker whether he takes up that question or not. Now for our speaker. Our keynote speaker for this evening is Dr. Srikanta Mishra, the Technical Director for Geo-energy Modeling and Analytics at Battelle Memorial Institute, the world's largest nonprofit private R&D organization. He's a recognized expert on integrating computational modeling and machine learning assisted data-driven activities for various subsurface energy resource projects. A renowned figure, Dr. Mishra also has been the recipient of 2021 SPE International Award for Distinguished Membership. Among his many laurels, he has also been the alumnus of celebrated institutes, which include Stanford University, the University of Texas at Austin, and our very own IIT ISM Dhanbad. Sir, I welcome you to our event here today. Welcome back to your alma mater. We are honored by your presence. You may
Thank you, Arslan. Thank you, Arslan. And thank you, everybody, for taking the time to join this 3-hour session on a Saturday. It is a matter of profound joy and pleasure for me to be able to give something back to my alma mater. And so what I have in mind today is sort of the distillation of our recent work in the area of data analytics. And this actually is a condensed version of the one-day short course that I normally teach for SPE. I taught one on Monday virtually for the SPE ATC in Dubai. And, it also forms the core of longer workshops, like a 5-day workshop that I will be teaching for Repsol beginning Monday. But what I've done is I've tried to whittle down the basics into a form that is easily understood and appreciated by upper division petroleum engineering students who are in their 3rd and 4th years. So that's what we will do during the first 2 hours in terms of taking a look at the terminology, at the rationale for using data-driven modeling, and then we will cover some theoretical basics. And then we will spend about an hour looking at examples and case studies. And then the final hour will be a software demonstration using an open source software package. So because you will have access to the recording, hopefully you can go back and kind of revisit the steps that I have taken. Because this is a short presentation, what I would do is I will have all of you put your questions in the chat box, and then before each break, I will set aside maybe 5-7 minutes to look at some of the questions and then answer them before we go to the break. With that, let me get things going. All right, everybody can see the full screen slides?
Yes, sir.
Yes, excellent. All right, so the topic of today's talk is application of data analytics in petroleum engineering. I don't need to go through the introduction. Just wanted to point out that in collaboration with Akhil Dattagupta, who's a professor of petroleum engineering at Texas A&M, our very own IIT ISM petroleum engineering graduate from the 82 batch, he and I put together this book, Applied Statistical Modeling and Data Analytics, written by practitioners for practitioners. So it's not like a typical book on statistics or a typical book on machine learning. It's really a very practical book for petroleum engineers and geoscientists. So I hope that your library will have a copy of this book. In any case, that's the book that I use as an informal textbook for my courses and presentations such as this one. So there is a lot of buzz about data analytics, and algorithms are taking over the world, if you want to believe the news headlines, whether it is in the field of consumer marketing, health and life sciences, politics, sports, you name it. And this new technology has been touted as a game changer over and over again. Now, in the oil and gas industry, we also collect large volumes of data about the subsurface, about the physical infrastructure and the flows therein. So the question naturally arises, can we also take advantage of this exciting new technology? And can we mine the data to obtain new insights about the reservoir? Can these insights help us increase operational efficiencies? In other words, can we convert data into actionable information or information that we can act upon? So that's the attraction, and that's also the challenge at the same time, because the possibilities are there. The question is, can we really make use of those potential? So let's talk a little bit about what exactly we are trying to do during the next 3 hours. So my goal is to provide really a practical introduction to applied statistical modeling and data analytics techniques. And in a way, this is what one would package into a one-semester course. And that's what we have done, for example, in a course that Akhil Dattagupta teaches at Texas A&M, in which I'm a guest lecturer. So basically, we combine both statistics and data analytics into a single course. And we start with foundational concepts. And then we go on to linear regression and variance for building simple input-output models. Then we move on to multivariate data reduction and clustering for finding subgroups of data that have similar attributes. So here we are still operating in the space of the independent variables. And then we move on to the more advanced machine learning techniques for regression and classification, which helps us develop more complex data-driven input-output models. So that's kind of the hierarchy of topics that we will visit. And at the final session, we will have a software demonstration using the open source software package called R. And then we will also be using Rattle, which is a graphical user interface that works on top of R, to showcase the application of machine learning techniques. And throughout this presentation, I will be emphasizing the practical aspects and not really the statistical rigor. So this is not a presentation about statistics or computer science or applied math. This is really about the application of those techniques for petroleum engineering problems. In terms of the timeline, so the first 45-50 minutes or so will have introduction and then statistical foundations such as regression analysis and multivariate statistics. Take a short break, come back and go through the basics of machine learning and then the case studies. and then take another short break and come back for the software demonstration part. And then we will do a wrap up. So let's begin with the concept of statistics, because that's really the foundation of all of our discussions. So what is statistics all about? It's about the translation of data into information. And this involves collecting data, summarizing data, and interpreting data. And that interpretation can be described in these three words. One is the structure that is within the data, if there are any trends in the data, and some quantitative formal relationships that can be extracted from the examination of the data. One thing to keep in mind that this quantification of the relationship between the independent and the dependent variables will require specifying the form of the model. So you postulate the form of the model, you use the data to estimate the coefficients of the model, and that is why it becomes a transparent model. In other words, it's what we call a white box model, because we can see through the model and we can clearly understand how the input variables are related to the output variables. In terms of big data and analytics, we are really dealing with two concepts. One is big data, the other is data analytics. So what do these concepts mean and why do we want to use them? With big data, we are referring to something that is characterized by the three V's: volume, variety, and velocity. Sometimes, people add additional things like value and veracity, but let's just stick to the main three V's. A volume, because our data sets are really getting larger and larger on a regular basis. Variety, because we not only deal with numeric data, the so-called structured data, but we also have the data, unstructured data that comes to us in the form of text, in the form of graphics, in the form of static and dynamic images. So the amalgamation of both of these kinds of data really adds to the complexity of the variety step. By some accounts, 70% of all data that is being generated is in the form of unstructured data, text and images. And that's the part which does not really get much attention. Everybody's focused on the numeric aspects. And then finally, velocity, because the advent of advanced downhole sensors has given us the ability to collect data at a much rapid speed, and so the velocity also contributes to the volume. So in this context, data analytics is a useful process that helps us examine the data, understand what the data says, and that's the statistical learning part, which gives us some sort of a predictive model. And then we can apply that predictive model to make better decisions. So we can say that data analytics is a process that helps us understand hidden patterns and relationships in large and complex data sets. If the data set were simple, if it were not characterized by the three V's, then a cursory examination of the data would reveal to us the patterns and the relationships that are present in the data. But in large data sets characterized by the three V's, we have to use a more automated, a more advanced process, such as data analytics, to sort of see through the data and extract useful insights. Now here, the thing to keep in mind, in contrast to what we saw in statistics, that the form of the model is a black box model. It's extracted by the machine, by the algorithm. It's not transparent. And so that is a fundamental distinction between classical statistics and the more modern data analytics. So once again, in classical statistics, we postulate the form of the model. It's a white box model. In data analytics, the form of the model remains unknown, and that's why it's a black box model. It is what is discovered by the machine. Now, a little digression about where exactly did the word analytics come from. And so it's interesting that it actually came from a paper by a professor of business called Tom Davenport, who's at Babson College in Massachusetts. And he wrote an article in Harvard Business Review, which is sort of summarized here. That in the business world, typically it's difficult to differentiate yourself from competitors based on what you have and what you're selling. And so what you need to do is you need to become an analytics competitor by using sophisticated data collection technology and analysis to really understand the entire value chain, beginning with manufacturing, to distribution, to marketing, to pricing, the full spectrum of activities. So from our context, let us just look at the definition of analytics as the combination of sophisticated data collection technology and analysis. Now, nowhere does it say that we need to use machine learning. In fact, many analytics applications are actually using classical statistics. So that's the kind of open mind you need to keep, because when you become a practitioner in analytics, you're just using all the data that you have at your disposal and all forms of analysis that you can come up with. So what kinds of analysis are we talking about? So once again, we have a hierarchy going from the simple to the complex. At the lowest rung, we have descriptive analytics, which could be simply visual examination of the data to understand what happened. Then we move on to a little bit more complicated, which is diagnostic analysis, which is simply a qualitative deep dive to figure out why did it happen. And then comes the quantitative part in predictive analytics, where we can build a model that will help us answer the question, what will happen? And then we go to the next step, which is prescriptive analytics. And here we can take the predictive model and basically use it in an optimization mode to figure out how can we achieve our desired target. So how can we make something happen? There are a lot of terms floating around: data analytics, machine learning, statistical learning, data mining, knowledge discovery, artificial intelligence. So I'd like to provide a little bit more clarity into this nomenclature, into the semantic mess. On the one hand, we have data analytics. On the other hand, we have artificial intelligence. In the middle, we have machine learning, knowledge discovery, data mining, statistical learning. So these are essentially equivalent terms. So the point here is to make a distinction between data analytics and machine learning and artificial intelligence. And that's basically what we will discuss now. So data analytics, as we have seen, is data collection and analysis to understand hidden patterns and relationships, whereas machine learning is just one of the many enabling tools in data analytics. So if data analytics is a larger process, machine learning is just one of the enabling tools. And what that involves is the building of models between predictors and response, between inputs and outputs, between dependent and independent variables. And most commonly, that is done using black box methods. Whereas in artificial intelligence, you're taking this predictive model built using machine learning, and then you're combining that with new data to make decisions without human intervention. And that's why it's artificial, because there is no human involved in the process. But if you add the possibility of feedback, and if you let the machine learn from the most recent examples, that's when it really becomes a true artificial intelligence application, because it mimics the activity of the human mind that we are always learning from our experience. So it's the experiential learning part that sometimes is missing with what we see in artificial intelligence applications today, which is just taking the old learning and then applying it in an automated sense. So being engineers, obviously we have to render that into a flowchart, and that's what we have here. So in step A, we have the data collection part. In step B, we have the inference of the rules or the predictive model building. And so together A and B make the data analytics part. And then machine learning is only the B part. And then you go to the collection of new data, the application of the machine learning model, and then making decisions, and then providing feedback. So that's all the realm of artificial intelligence. So I hope that this clarifies a little bit with respect to the semantics as far as data analytics versus machine learning versus artificial intelligence is concerned. The data analytics process has three main elements. One is exploratory data analysis. The second is unsupervised learning. And the third is supervised learning. So let's talk a little bit about supervised versus unsupervised learning. So in supervised learning, when we have data, we will also have some sort of an annotation. It's either a quantitative label. It could be the weight of the apples that are shown here, or it could be some categorization which just says that, okay, these fruits are apples. And so we can build a model that says, given some information about the nature of these objects, we can come up with the prediction, whether it's an apple and what is the weight of the apple, for example. In unsupervised learning, we are only working in the space of the input data. So if we have a large number of different objects, so here apples, bananas, and oranges, then we can use some sort of a model to distinguish the different categories and separate them. So the apples are in one bin, the oranges are in another bin, and the bananas are in a separate bin. So in oil and gas exploration, there are a number of different areas in which these techniques have been applied. In exploration, for example, people have used these to find hidden patterns in large geologic data sets. In reservoir management, the goal has been to identify factors that lead to improved performance, either at the well scale or at the entire field scale. In proxy modeling, we want to take the output of full physics models like reservoir simulators and create fast system emulators, which can run in seconds as opposed to hours. And then we can use these more efficiently for repetitive tasks like history matching, like uncertainty quantification. In performance forecasting, we want to make real-time predictions of system response, whether it is drilling rate of prediction, whether it is the response of fluid injection like water floods to oil production in a neighboring well. And then in predictive maintenance, we look at how can streaming data from a number of sensors be combined with past performance to predict potential failures. So in all of these applications, we're looking for a reduction of cost, for improvement in productivity, for increase in efficiency. So these are the metrics that the decision maker, the manager, will be looking for with respect to the value-added proposition of this new technology. So as analysts, as practitioners, don't get overawed by the fact that, oh, I'm using this cool technology to do this cool analysis. At the end of the day, if it does not contribute to a business added value, then it's really not going to be very attractive from the perspective of management. In a recent article, we looked at, how has the number of papers in one Petro database grown in machine learning. So you can see that in 1990, if there were about 50 papers, then in 2020, there were more than 5,000 papers. So there's really been an exponential growth in machine learning applications. Here are some examples, and I'm not going to go through them in great detail. I'm sure that when I share the slides with you after the end of the day, all of you will have access to this slide. And you can see that there are a number of different use cases which come from not just our experience, but also the experience of others. And this is what I call analog learning. So when you see somebody using a new technology in a particular way, that sort of immediately triggers a response that, aha, hey, maybe I can also apply it to my data sets in this format. All right, so so that was sort of a quick introduction to the terminology and basic concepts in machine learning. And now I want to step back and look at the statistical foundations, which comprise of two topics. One is basic regression analysis, and the other is multivariate statistics. And the reason why I'm doing this is imagine if somebody asked you to start building a reservoir simulation model, and you have not even taken a reservoir engineering class. So the foundation is not there. And that's precisely the point, that machine learning is not a standalone discipline. It requires some fundamental understanding of basic statistic concepts. So in linear regression, and many of you should be familiar with this based on classes in statistics that you've taken or you will be taking. So in linear regression, we have data pairs x1, y1, x2, y2, xn, yn. We postulate a model that y is equal to alpha plus beta times x plus some epsilon, which is the error. That is the unmodeled error with a normal distribution, mean zero, standard deviation, sigma. So we estimate the parameters alpha and beta by minimizing a loss function, an objective function that minimizes the difference of the sum of squares of the residuals. And these residuals should be normally distributed with mean zero and standard deviation sigma. What is important is, we've already postulated the form of the model. We have already made the assumption that the residuals have a certain distribution. So that is what we need to test as soon as the model fitting is done. That, what is the trend in epsilon, the error term, versus the independent variable? Is it non-random? Is it cyclic? Is it monotonic? Then the linear model is not appropriate. So here's a simple example looking at initial well potential as a function of net pay. There is a trend, but there is also considerable scatter in the data. And this makes sense because clearly, the well potential should also be dependent on things like permeability, in addition to the thickness. But nevertheless, there is a relationship. We can capture that relationship using this trend fitting functionality in Excel. So let's take a look at what the output really tells us, and mostly I've seen people just generate the output and not look at the statistics to understand, what are the results telling you. So this is sort of a one-slide cheat sheet of how to examine regression outputs. So basically, what you will have is, let's see here. So you will have the multiple R and the R squared, which is the fraction of total variance explained by the model. And then you have the standard error, which is the estimated standard deviation of the error term, which is approximately equal to the RMSE. So most of us are familiar with the RMSE. And then you look at these coefficients. Now, most of the time, we will just focus on the value of the intercept and the value of the slope, but there is also a standard error associated with that. So what these two are is that they're saying that our regression coefficient is not a single value, but it's really a random variable. And the mean estimate for that coefficient is given by this column, and the standard deviation is given by this column. So then we calculate the t-stat, which is the coefficient divided by the standard error. And the implication here is that the bigger this value, the better off you are, because you take this t-stat and then you convert that to the p-value. Now, everybody's heard of p-value, particularly in the context of public health and statistical tests of significance. Now, I'm not going to get into the null hypothesis and all that good stuff. Leave that to the statisticians and the applied mathematicians. But basically, the interpretation of p-value is that you want that number to be as small as possible. The smaller, the better, because the smaller that number is, the higher the chance is that this coefficient is statistically different from zero. Otherwise, you will say that, okay, I don't know whether it is statistically zero or similar to zero. So that's why you want this number to be as small as possible. You want the t-stat to be as large as possible. And then you can calculate the upper and the lower confidence intervals, and roughly these are plus or minus 2 standard deviations away from this estimate. So that's kind of the quick overview of a regression analysis interpretation. We also do diagnostic plots, and the first one is where we have the observed versus the predicted. This is the anchoring 1:1 line, slope 45 degrees. Everything should fall on it if the model is the right model. And if the model is not an adequate one, you will see, first of all, some scatter. You will also see a slope that is different from the 1:1 line. Then you look at the residuals, and basically you want this residuals to be distributed in some random manner. Here we see that the spread of residuals at low values of X is a little bit more than the spread at higher values of X. And that also comes through when you make a normal probability plot of the residuals, and all of this should align on perfect straight lines. So there are local deviations, but all in all, it seems to be a reasonable fit. It's not an excellent fit. It's what I would call a reasonable fit. So those are the kinds of diagnostic plots that you need to look at, as opposed to just clicking one button, getting the results, and then being satisfied with it. Nonlinear regression works in a similar way. The difference is that now you're using these transformations, G of X, Y, G of X, and F of Y, to make everything similar to a linear regression approximation. And here, these Fs and the Gs are linearizing transforms, which could be logarithmic, which could be exponential, which could be power, which could be non-parametric, and so on. Multiple linear regression, just an extension of what we saw for the one variable case. So you have multiple variables and you have these additive terms. You can make it more complicated by saying that I not only have B1x1 and B2x2, I can also have B12x1x2, these interaction terms, or I can have quadratic terms, B11x1 squared. When we have multiple variables, the question is, do we need all of them? Are these all statistically significant? And that is what is answered by this Ataiki information criterion, which is really seeking a parsimonious balance between the goodness of fit and model complexity. The goodness of fit through this term, which looks at the residual sum of squares and the number of observations, and model complexity through the number of model parameters. So whether you have 2 variables or whether you have 7 variables. And the question is, are you getting what's called enough bang for the buck as you increase the number of variables? Your R square might go up just a little bit, but is that sufficient increase given the additional complexity of the model? And that is where you want your AIC to be minimized. And here, for example, we're looking at one case where we have a model for predicting permeability from well log attributes. And if I have the full model with all 7 well logs, I get an AIC of 383.7. And as I systematically drop each variable, then I see which one amounts to a reduction in AIC. I see that this sonic log DT is the one that does that, which means that I can basically get rid of this variable and still have a similar performance. So key takeaways: first, plot the data. Second is model structure is important. You may need to experiment with multiple models for the best fit, and not just simply assume that alpha plus beta x is what is the most appropriate one. It could be beta times x to the power of 2/3 or square root of x or log of x. Then you want to understand the distribution of residuals and make sure that that is indeed random. Examine the significance of regression coefficients using the table that I showed earlier. Check for parsimonious outcomes using the Ataiki information criterion. And then, the other picture is, we often assume that all of our data belong to one statistically homogeneous population. It could be that the data can be partitioned into subpopulations. For example, if you have data from sandstone and carbonate reservoirs thrown into one data set, you may wish to separate them into 2 groups before doing your regression analysis. So that's kind of the idea here, which is our segue to the multivariate statistics part. But before we go there, we have one other thing to consider is the data plotting part. And all of you should be familiar with simple things like scatter plots between 2 variables. And here is the extension of a scatter plot matrix, a multivariate scatter plot, where, in this particular case, we are looking at 3 response variables and then 4 independent variables. So these are the design variables. These are the performance metrics. So this is the citation where the study is described. So basically, you have a matrix of scatter plots between all of the variables, and then you have typically a scatter plot, smoother, a line that goes through the data point, sort of to visually anchor the trend. Here, for example, you see that there is sort of a thresholding effect, and then there is a nice linear monotonic relationship. Here you see that there's essentially no relationship. And here there's a linearly increasing relationship, and then it sort of plateaus. Here there's a negative relationship, and so on. So that's the scatter plot matrix. And then you have this correlation bubble plot. So when you have 2 variables, you can calculate the correlation coefficient in Excel. That's the function correl. But there is also a more advanced version of the correlation coefficient. This is called the rank or the Spearman correlation. Otherwise, the basic correlation is the Pearson correlation. So this is more of a robust measure of the strength of association for both linear and nonlinear relationships, because the Pearson correlation coefficient actually works best for linear relationships. And so what you do is you rank the samples from the smallest to the largest, and that helps identify both the redundant variables and the relevant variables. And in machine learning or data analytics terminology, this is referred to as feature selection when dealing with large data sets. And the correlation coefficient is just one of the many possible approaches. So here is a reference that can take you to more complicated feature selection methods. But in this data set, which is where we're looking at the minimum miscibility pressure of CO2 in the context of CO2 enhanced oil recovery. That's the pressure at which CO2 and crude oil will form a perfect mixture, and obviously that depends on 2 things. It depends on temperature, and it also depends on the composition of the crude oil. So the composition of the crude oil is given in terms of C1, C2 through C6, and then C7 plus. It's also represented in terms of the volatiles and the intermediates and the ratio of the volatiles to the intermediates. We have one additional variable, the API gravity, which is related to these 2, the molecular weight of the C5 plus and the molecular weight of the C7 plus. So when you look at this matrix, you can basically see, for example, here, that the you want these bubbles to give you a correlation coefficient of 1 along the diagonals, because that's the correlation of all the variables with themselves. But then the off diagonal ones are the more interesting ones. So somebody just muted me. How is that possible? All right, what I was saying is, when you look at the off-diagonal terms, you want to see where are things lining up. So C2, C6 seems to be highly correlated with the intermediate ones. MWC5 seems to be highly correlated with MWC7 and API. See the volatiles are highly correlated with the volatile to intermediate ratio and the C1. So that is what helps you figure out what are the redundant variables, because you don't need to carry all of these variables. Only one of them will be appropriate for your additional analysis. The same thing with respect to relevance. So if you go down this column of MMP, you see that temperature seems to be a relevant one, and all of these seem to be relevant. And then as you go to things like MWC7, the size of the bubble drops off, which means that it's probably not as relevant. Okay, all right. So next we move on to multivariate analysis. What time is it? So now we look at multivariate statistics. So principal component analysis. This is a statistical technique for reducing dimensionality from making data independent of each other without any significant loss of information. So if you have 200 variables, then clearly there's going to be some dependence or some influence that that multiple variables have on each other. And so how do you capture that, and how do you come up with a reduced set of variables that will preserve that information without having that number of variables? And I will show you with an example. So this is where, you know, from your applied math classes, if you've gone through eigen analysis, this is basically the application of an eigen transformation. So the principal components are formed by weighted linear combination of the original variables. So there's a rotation and projection, and we are transforming into a new set of coordinates, which maximizes the variance and which are also mutually orthogonal. So that's the other advantage part, is that if we have x1 through x20 and there's some dependence across each other, it makes difficult to parse things. Whereas now we go to some new coordinate set, x prime, y prime, and x prime and x1 prime and x2 prime, which are going to be totally independent of each other. And that way we have some separation of influences. So these principal components can be interpreted as surrogate variables. So we have gone from the space of one set of coordinates to another set of coordinates. Not going to spend too much time on the mathematical details other than to say that, okay, these are just linear combinations of the original variables, and the weighting factors are calculated from some eigen analysis. And I will show that with an example. This is how you go from the raw data to standardization by subtracting the mean and dividing that by the standard deviation, so that all of the variables have basically the same dimensionless units. Then from your correlation matrix, you can calculate the eigenvalues. So if you have three variables, you're going to have three principal components, you're going to have three eigenvalues. Each eigenvalue is the fractional contribution of the total variance. So if the total variance of the data is given by proportional to 3, then 2.685 divided by 3, which means that 90% of the variability in the data can be explained by the first principal component. When you plot the principal components with respect to their eigenvalues, and you will see sort of a drop off with respect to the fraction of contribution towards the total variance. And you want to say that, okay, do I need all 7? Or if I'm just interested in the top principal components that explain like 90% of the variance, then let me do that. So this is how you calculate the eigenvectors. And the eigenvectors are useful in terms of calculating the principal component scores. So instead of the actual values of the standardized values, now you have the principal component scores. And these principal component scores are going to be calculated as shown here. So here is an example of a data set that we will be working with in a little bit. It's a 5-variable data set where we have these logs: gamma ray, log 10 of the LLD, the bulk density, the neutron porosity, and the photoelectric log. And then these are related to permeability. But here we are in the space of just the input variables. We are calculating the principal components. So these are the principal components. These are the weights that go towards calculating the principal component scores. And this is the variance associated with each of the principal components. So what we can see is that the first two principal components capture something like 75% of the total variance. The top three, something like 88%, and then the bottom two, the rest of the 12%. If you go down this column, you will see that the principal component 1 has 3 major components: log 10 LLD, rho B, and neutron porosity, whereas the second principal component depends on gamma ray and photoelectric. So what we have done is we really we've really recombined everything in a way that sort of separates out the variables. We have not dropped any of the original variables, but with two principal components that explain 75% of the variance, we can somehow reduce the dimensionality from 5 to 2, because each principal component now has, this set of variables to influence it, and the second principal component has this to influence it. Principal component analysis goes into the next step, which is cluster analysis. And the goal here is to group objects that are similar based on some measured characteristic. This is unsupervised classification because we are also in the space of independent variables. So you go from this cloud to these three distinct clouds. Of course, Mother Nature might not be so favorable at all times to give us this clean of a separation. But that's what we want to do, is we want to use statistics to create these groups as opposed to using domain knowledge to create these groups. Now, when you have a large data set, domain knowledge might not be very helpful, which is why statistics can help us in separating these out, saying that from a statistical standpoint, this subpopulation is distinct from this subpopulation, is distinct from this subpopulation. So if we have to do any model building, then we should be doing that using each of these subpopulations as opposed to throwing everything into a large single population. So k-means is one common technique where you look at the distance between pairs of points, and then you move them from maybe this cluster to this cluster, so that it's for example, if a point is here, then instead of putting it in this cluster, you would put it in this cluster because it would be closer to the centroid. And that's kind of the idea, that you want to make each of these clusters as tight as possible. You want to make these two as separated as possible. And that's how the math works out. So you capture that using a graph like this, which basically says that as you increase the number of clusters, your sum of within cluster squares goes down. And based on this plot, you would say that, okay, for this data set, I need between 4 and 5 clusters. So here is how it looks if you have 5 clusters. Now, remember, we are actually in a 5-dimensional data space, but we are plotting it in the space of the first 2 principal components. So it may not look perfect, but this is really the rendering as it is projected into this space. And here is how you can group them based on their proximity to the centroid of that particular cluster. And sometimes, in the context of log analysis, these are called electrophases as opposed to actual lithophases. We also have this technique called hierarchical clustering. This is where you create a dendrogram, and you start by putting each observation in a separate group, and then you take the clusters and then you progressively merge them until all observations are in a single group. And so you have some sort of a dissimilarity measure, and based on that, you figure out, okay, how many clusters do you need? So if you draw the line here, then you'd say, okay, I have 1, 2, and 3 clusters. Or if you draw the line here, you'd say 1, 2, 3, 4, 5 clusters. So the key takeaways from these segments are that we have different possibilities for data visualization, and I've shown you hopefully 2 new ones: the correlation matrix and then the scatter plot matrix. Principal component analysis is a useful tool for reducing data dimensionality and identifying surrogate variables. So I will sort of revisit that in a little bit as well. But cluster analysis is a technique that builds upon principal components to group data into statistically homogeneous populations for model building. So that's the other important thing, is that oftentimes you have a large data set. And so when you have a large data set, you want to look at 2 things. You want to look at the space of the independent variables to see if there are redundant variables that should be taken out. And that is where both correlation analysis and principal component analysis can be useful. And then you also want to see if there are groups within the data, and groups could be because you have different rock types, you have different data from different time periods, you have data from completely different geologic environments or operational conditions or pressure and temperature regimes. So whatever it is, this is the automated technique that really helps you understanding whether the data should be partitioned into subpopulations before you go into the model building part. And that is why these techniques are very useful as a first step in determining the structure within the space of independent variables before you start building your input-output models. All right, so that takes me to my my break time slide. But before you all get up and go, let's take a little bit of time to see if there are any questions. So where is the, do we have any questions in the chat box?
Okay, so we are open to queries now. Anybody who has a query can raise their hand if they cannot find the chat box option.
There's a lot of material to cover, so I know I went a little fast, but you have access to the recording, so you can always slow it down and then play it at your own disposal. I will share the slides with you. Oops, not yet. No.
Recording of the session will be uploaded on SPE IIT's YouTube page, and the material will be uploaded too. So you can use it whenever you want. So there's a question.
There's a question? Yeah. Will you
I'll
read
it out for you. Yes, sir. So in machine learning, you said it is black box. Without knowing the details, how can the user decide which model is suitable?
Yeah, we will address that in the next segment as to how do you go deeper into the model and how do you make sense of what the black box is trying to tell you.
Sure.
All right. If not, it's 9:25 by my watch, which means it's what, 6:55. So let's take a 5-minute break and then come back. Yeah.
Yes, sir.
Ishika, if you can keep track of any other questions that show up and then kind of bring them to my attention during the next break.
Sure. Sure, I'll keep the track of.
Okay. Okay.
An announcement for everyone in the meet. If you aren't able to view the chat box option, you may leave the meet and rejoin the meet. And if that's not fine by you, you can raise your hand and I'll take your question.
Sir, you can unshare your, slides, etc. Because
Sorry, I was looking at my email and so you probably didn't see my slides, but
no. Yeah, your email was visible
Yes,
to everyone.
can,
That's why I told you that.
Yeah.
Yes, so you can
Yeah,
unshare your
hopefully.
screen for the time being. And,
Yeah, hopefully there was nothing bad on my email list.
No, it's okay. It's okay, sir. It's okay.
I see somebody has a hand raised, Raj Kiran.
Yeah. Good evening, Dr. Srikanta Mishra. So
Yes.
my name is Raj Kiran and I am currently assistant professor here in ISM. I had just like a small question related to
Sure.
data analytics. Like, what is the future you see for the data analytics currently? Like, so what
let
is the focus? Is it about reducing time or what?
let me kind of revisit it at the end, because it's one of the things I want to come back to as to where things are with the application of data analytics.
Thank you.
Yeah, right now there is a lot of excitement because it seems to be applied all over the place in areas like consumer marketing and health and life sciences, etc. But the thing is that they don't have any alternatives. They don't have any physics-based models or mechanistic models that they can use to capture human behavior. So they have no option. But in the field of subsurface energy resource management, there are clearly a number of physics-based models that have been used, that are being used. So, people are sort of beginning to think about what is the nature of these new techniques and how can they be used in conjunction with what we've been using so far.
Thank you.
All right, shall we get started?
Yes, sir.
So there are two more questions in the chat box. Shall I read them out for you?
Yeah, please.
So there's this question. Can you make the difference between PCA and bubble diagram more clear?
The bubble diagrams are looking at just two variable correlations. So, so you're only looking at the correlation between any two variables. That correlation quantification goes into the principal component analysis, and it helps create these surrogate variables that are really combinations of multiple variables. So in the correlation analysis, you're only in the space of two variables, any two variable pairs at one time. In principal components, you want to look at the effect of multiple variables that might be acting together. Any other questions?
And there's this question. Yes, sir. So there's this question. Like academically, we are being told to like pursue our careers in the core petroleum industry, not the data analytics. So this person asks, how do we like make a smooth transition from the core industry to the data analytics area?
Well, that's kind of an interesting question, because I am not here to promote data analytics as an alternative career. I'm here to promote the use of data analytics as a powerful tool on the oil and gas industry. So if you want to be a data analytics person, then you better change your careers and then go get a degree in data science and take that path. There is no easy way out. You cannot learn data science by watching a couple of YouTube videos and then borrowing a few scripts from GitHub and then saying that, okay, that's it. I am now a qualified data scientist. No. My point in this talk and in all the talks that I give is that I would like petroleum engineers and geoscientists to be more educated about this new technology. There was a time when geostatistics was very new. Nobody knew, what geostatistics could do, but we all read up about it. We all learned about it. And so it became a part of the curriculum. And there was a time when numerical methods were not part of the petroleum engineering curriculum. Strange as that might sound, you go back 80 years and it was all analytical methods. So here's a new technology. And so what we need to do is we need to embrace it. We need to understand it. We need to internalize it. And that is what you will see throughout this presentation is not how to be data scientists, because there is a different pathway. But the pathway that we are following, that I would like to recommend, is stay in your profession, but become a more educated petroleum engineer by learning about data science. Within petroleum engineering, you can do lots of things. You can be a simulation person, you can be a well test analysis person, you can be a drilling person. And similarly, you can be a geostatistics expert, you can be a geoscience expert, and you can also be a data science expert. All right, let's get started on the second component, which is going back from statistics to the data science part. Come on. All right, so in this segment, we're going to talk about some basic concepts of machine learning, and then we will look at some case studies and examples. As we saw earlier, in classical statistics, we begin by postulating a model between the independent variables and the dependent variables. The independent variables are also called predictors. The dependent variables are also called responses. The independent variables are also called inputs, and the dependent variables are also called outputs. So what we have seen is that in the presence of complex multidimensional data sets, we need to look beyond linear regression or variations of linear regression, because these are not adequate anymore. And so the idea that has emerged and has become more mainstream is how can we extract the model from the data without spending a lot of time trying to figure out the underlying functional form. If you have two variables, you can do these experiments. Y is a function of alpha plus beta times x, or beta times log x, or beta times square root of x. But if you have 20 variables, those permutations and combinations will be too much. So the idea is to let the algorithm take that trouble and to figure out on its own what that functional form is. And that is where the black box nature of the model comes in. So we will not worry about the exact functionality that goes into the model. There are two kinds of problems in this context. We have regression problems where the response variable is continuous, for example, permeability, for example, production rate. Or we have classification problems where the response variable is categorical, such as rock type, such as two states in the operation of an equipment, like the pump has failed or the pump is normal, or the quality of the fit of a model, whether the fit is good, whether the fit is bad. So that is how we have to sort of broaden our problem definition, that on the one hand, we have continuous responses, and on the other hand, we have categorical responses. So let's take a look at these two different types of problems. So in classification, we have these two groups. So we have these two groups, and we want some decision rule that helps us separate group 1 from group 2. So the outputs are categorical. All we know is that we have this, circles versus the pluses, and those are the two class labels. And then within the circles, we can say that, okay, they all have individual numerical values. So we can create a regression model where we are looking at the actual values. So the outputs are continuous versus the outputs are categorical. Now, why machine learning models, and when should we be using them? So historically, subsurface science and engineering analysis have relied on mechanistic models. For example, Darcy's law. For example, Poiseuille's law for flow through pipes. And that's because they incorporate causal input-output relationships. So there is some mechanism, some physical mechanism, some geologic process that goes into the relationship between the input and the output, and that is explicitly stated in these mechanistic models. So, that is why typically what we see is that experienced professionals who've been working in the industry for a long time, they are wary of purely black box machine learning models that do not have any such domain level understanding. So that's kind of the problem that I referred to earlier. In the case of Amazon, in the case of Netflix or Google, they don't really have any mechanistic causal input-output relationship that says, okay, if this is the person who's sitting at a hostel room at ISM and going through the Netflix selections, then that person is going to select these movies. That sort of model is not existent, and what that means is that you have to rely on purely black box models. In our industry, we already have a number of mechanistic models which incorporate these causal relationships, and so there's some hesitation, but the use of machine learning models can be justified in cases such as when the physics-based model is computation intensive and or immature. So when you look at unconventional shale oil and gas wells, the flow process begins with nanoscale pores and then move to the well scale. And obviously, as you go from the pore scale to the core scale, the field scale, you're going through a lot of processes that are not very well understood, that are not very well represented through constitutive relationships. And so one could say that the physics-based model is immature. And even if you do put in some processes and then you start coupling things like multi-phase flow with geomechanics, then the whole model becomes very computation intensive. So that's a situation where you could say that, okay, let's try by just looking at the data and see if we can extract some insights in a reasonable period of time. The second situation is where a suitable mechanistic modeling paradigm does not exist. And once again, if you're looking at some process across scales, that's where the modeling paradigm may not even exist because people have not done experiments at all of the scales and have understood how to bridge the physics across scales. So in a recent paper in Science magazine, Elizabeth Holm was articulating the case for black box models. And so we kind of use that in a recent paper in the JPT to elaborate on these cases. So these three cases can be described as follows. So first, when the cost of a wrong answer is low relative to the value of a correct answer. So that is when, even if you use a quick and dirty black box or a data-driven model, you can get away with it. For example, in history matching, what do? You do a number of model runs, and in each model run, you're trying to come up with model predictions that are as close as possible to what was observed in the field. And to do this, you have to adjust parameters. So if you have hundreds or even thousands of model runs to make with a physics-based simulator that takes hours, if not days to run, then clearly this is infeasible. So what you do is you set up these proxy models that may not be 100% accurate, but even if they are 90% accurate, they can help you zoom in the correct parameter subregion, where you can then turn to the physics-based model for more accurate estimation of the parameters that lead to the best history match. The second example is when black box models produce the best results. And here, the example would be that, let's say you have a well-test response and you plot your derivative, and then you start looking at some library of already pre-identified derivative responses that match some sort of a conceptual model. Now, if you have hundreds of these images, then clearly the human mind sort of starts getting bogged down after some time. So the automated parsing of image libraries for identifying the best image that matches what was observed is where machine learning and image recognition techniques can really work very, very well. And so that's the second case. The third case is as tools to inspire and guide human inquiry. And typically these are conditions where a mechanistic modeling paradigm may not exist. For example, you are collecting data about the failure of an ESP, an electrical submersible pump. And so you have all the mechanical and the electrical attributes, and then you also have the flow conditions. But obviously there's no model that says, if your electrical and mechanical responses are this and the flow conditions are this, then you're going to be your pump is going to fail. So that is where having a purely data-driven approach is going to be helpful, because they can point to conditions which are adverse and conditions which are favorable, and that way they can point to new ways in terms of best practice as far as operations are concerned. So what are the key concepts as far as building these black box models, building these data-driven predictive models are concerned? We need to have some understanding of what are the modeling techniques that are at our disposal and how to select one or more of these. How do we evaluate the model and how do we validate the model? Because that's the important part, is we are always in the danger of overtraining or overfitting the model, because they may have too many degrees of freedom. And so we need to make sure that when we train the model with one set of data and then we try to predict them, at least in some blind prediction mode with another set of data, there will be some robustness in terms of model performance. The models of today have a large number of user adjustable parameters. So to what extent can we automate the tuning process? In model aggregation, we're looking at the fact or the possibility that there could be more than one model that seems adequate. And then the question comes, how do you combine them, or how do you aggregate them to make predictions, to do an understanding of what the models are doing? Variable importance is where we slice and dice through the model architecture to get an understanding of the relationship between the input variables and the output variables, and sort of go beyond the black box to gain an internal understanding of the inner workings of the model. Now, the first set of remarks I have are for regression problems, and then I will make some comments about how these can be extended for classification problems. So in terms of predictive modeling methods, we have a number of different choices: regression and classification tree, random forest, gradient boosting machine, support vector machine, artificial neural network, and Gaussian process emulation or kriging. Now, this is by no means an exhaustive list of everything that's out there, but these are the most commonly used techniques. So in the next set of schematics, just wanted to take a few minutes and kind of explain the fundamental ideas behind each of these methods. So in regression and classification tree, what we are doing is partitioning the parameter space into rectangular regions with constant values or class labels. So if we have permeability as a continuous variable, we will just group that into 4 regions. So let's say R1 is permeability greater than 1 Darcy, R2 is permeability between 100 millidarcy and 1 Darcy, R3 is permeability between 10 and 100 millidarcy, and R4 is anything less than 100 millidarcy, 10 millidarcy. So basically we've made the problem coarser, but that's by design. The other option is to say that, okay, if we have 4 classes, rock type 1, 2, 3, and 4, then that is how we can set up this process. And once we have done that, we are looking for decision rules that will take us from the value of one variable in combination with the value of a different variable to that region. So we can say that if x1 is less than some threshold t1, and x2 is greater than some threshold t2, then we will be in the region R2. Now, clearly, this is very easy to understand and very easy to communicate. So that's the advantage. But the disadvantage is because we have such coarse representation of the parameter space, the accuracy is going to be compromised. But if we take a large number of trees and then we combine them into a forest, then perhaps the accuracy is going to be improved. And that is what we have in random forest, where we are building an ensemble of trees. We're building a collection of trees using random subsets of observations and predictors. What that means is that every time we build a tree, we don't use all of the data. We use only a subset of the input data, and we use a subset of the predictors. So we are essentially looking at incomplete perspectives. We're looking at multiple perspectives. It's kind of like going around the elephant with blindfolds and touching the elephant in different parts of the body. So obviously each touch is inadequate with respect to identification of the animal. But when you put all of those observations together, you start getting a composite picture that is more accurate than any individual picture. And that is precisely the idea here is, instead of a single tree, if you have a large number of trees, you get a much better perspective on the overall problem. And in fact, it has turned out that the random forest is a very robust and a fairly accurate method with respect to predictions. In a gradient boosting machine, we build a sequence of trees that address the shortcomings of each previous tree. So it's kind of like building a linear regression model. Then you look at the residuals, and then you build a model for the residuals. And then you put them together and look at the subsequent residuals, and then build another model for those residuals. And then when you combine all of these, you have a model that really works quite well. In support vector machine, we go from the input space to a higher dimensional input space where things are separable using linear planes and linear surfaces. And we can also use concepts from linear algebra to build a relationship. And the SVM has also been shown to be quite accurate. In artificial neural networks, we are trying to mimic the functioning of the human brain. So we have these inputs, which could be individual well logs, and then we process them through an input layer, meaning that we're taking weighted linear combinations, and then we are processing them through some nonlinear transformation, and that gets into another layer. And there also we do a weighted linear combination of everything that comes in, and then we do some nonlinear processing that goes to the output layer, which would come out in the form of a prediction that is a lithofacies. So really we are trying to mimic how the human mind works, and so get to these results. Gaussian process emulation is the same as Kriging that we all know and love in geostatistics. Basically, it's a multidimensional interpolation methodology that looks at the trend and the autocorrelation structure of the data. And the only difference is that in kriging, we have 3 spatial coordinates as the independent variables. And here we have the actual physical variables as the independent or the predictors. Next, we move on to the model evaluation. So on the left panel, I have this case where, the basic the actual true function is given by this dashed line. So when you sample it and then you add some noise, you get these individual points. And obviously it looks very noisy, but it's around this original trend. And if you were to fit that trend in a very accurate manner, you would get this red line. And if you make a plot of the true versus the predicted, you'd get a very nice fit around the 1:1 line. But in actuality, what you've done is you've basically fitted the noise in the data, and you're not fitting the quadratic trend, but you're fitting a a polynomial model of some higher order that may or may not give you good accurate predictions when you're away from these training points. So the takeaway is that model overfitting is likely if you evaluate the model solely against the training data set. I'm going to skip this slide, but just show that, on the one hand, as the model complexity increases, your model performance seems to get better, your error reduces. But as your complexity increases and you start making predictions away from the training data, your variance increases, meaning that you're likely to make wrong predictions. So there is some trade-off between what is the complexity of the model and what is the accuracy that you get, and that's kind of what the Akaike information criterion also tells us. These are the standard goodness of fit metrics, and ideally you would apply those to an independent data set after you've built your model with some training data. But unfortunately, that may or may not be possible. So here is a clever way of taking your original data set and then creating an independent data set or a pseudo-independent data set using this process called cross-validation. So let's say that you have this original data and then you divide it into 5 subgroups. And when you train on only 4 of those subgroups and then predict on the held out subgroup. As you go through the cycle and each time you take out a new 1/5 that was not included in the training set before, and you do the predictions, and when you put these together, what you do is recover the full data set. So you've made a full data set of predictions where none of these points was included in the training set. So that is what is called cross-validation. It's a very clever way of getting to a pseudo-independent data set. General logistics of model fitting. The main point here is that you use the validation set. So you split your data into training and validation, or training and testing. So the testing data set is really to come up with the best estimates of the independent parameters. And you want to have some robustness in those fitting, because as you make those parameters such that the model becomes more and more complex, your apparent R-square will keep on increasing. But when you do it, when you do the cross-validation, you will see that there is some sort of a plateau, and then you fall back in performance. So you want to select some optimal level of performance, and once you've done that and you've gotten the final tuning parameters, then you refit the model with the entire training set. A listing of the tuning parameters for various methods. Then moving on to the question of model aggregation. And model aggregation is important because when you measure the model fit in terms of training or test error, you can see multiple competing models. And here is an example. So we have the cross-validation standardized RMSE for a number of different model fitting techniques. So we have ordinary kriging, then we have universal kriging, just a quadratic model with constraints, some adaptive spline fitting, and then this is a non-parametric regression. So you see that at least 1, 2, 3, 4 cases, the black bar seems to give you the best performance, which means that they are all equally acceptable in terms of explaining the model. And so what we want to do is, rather than take any one of these models, we want to aggregate over a large set of acceptable models, because it will help us get a better understanding, a robust understanding. It'll also get us a robust set of predictions. Not only that, what we have seen in data science competitions is that the ensemble models, where you aggregate the predictions, are actually systematically top performers in these competitions. In terms of ensemble modeling methods, we have simple averaging, we have weighted averaging, we have stacking. And so in this recent ERTEC paper, we talked about these methods, whether you just take the arithmetic average of all of the models, whether you take the weighted average, for example, you take weighted by the inverse of the RMSE. Why inverse of RMSE? Because RMSE is a measure of the error in the model. So the reciprocal of the RMSE is really a measure of the goodness of fit. And so you can weight the models by that. Or you can do this process called stacking, so which becomes a two-stage model building process, where you take the predictions from the individual models and then you combine them through some sort of black box method, and that helps in improving the accuracy of the overall model. These are not new ideas. They come to us from the field of watershed hydrology, where people have been building these rainfall runoff models. So you have a certain volume of rainfall, and then that leads to a certain volume of runoff, the rest of which goes into the ground via infiltration. So there are lumped parameter models, and it turns out that because the models are so simple, many different combinations of the parameters will give you the same rainfall runoff relationship. And so we go from having one true model, one acceptable model, to a whole host of acceptable models. And that's the concept called equifinality, meaning that there's non-uniqueness, because you can get to the same final state by starting from a number of different initial states. And so that is what's been called the generalized likelihood uncertainty estimation, or the GLUE framework. Variable importance. This is important for understanding how the black box model works. So obviously, some of the techniques like random forest or gradient boosting machine have algorithms that have specific importance metrics. But they're not always consistent across models, because they take different approaches for handling variable interaction. So we have come up with this method called R-square loss, where we start with all variables in the model. We calculate the R-square, and then we drop each variable one at a time. And we look at the loss in explanatory power, the loss in R-square, by dropping each variable, and that is what is the R-square loss for that particular variable. So obviously, the higher the R-square loss, the more important the variable. And this turns out to be a very simple and intuitive model independent measure. You can show the results simply as a collection of bar graphs. And let's say we're looking at the green graph here, which is just one of the many models that we were considering. And so the anisotropy ratio is more important than injection rate, which is more important than caprock porosity or reservoir porosity. The mean reservoir permeability and the reservoir thickness are also important. Here is a very interesting book available online on making machine learning models interpretable. And we have a number of different techniques that can be used for this purpose. What I was describing is what's called remove in this terminology of the book, but there are other methods that you can also use to quantify the importance of different variables. So far we've been talking about regression problems. Let's talk a little bit about classification problems. The goal is to use the predictors to determine a group label for the observations. The response is categorical. The predictors can be categorical or continuous. So I will have an example in just a little bit, so you can better understand what the classification problem and what the categorical variables could be. we train the model using data, and then we need to figure out how to do the model evaluation, because there is no R-square here. So one of the challenges is class imbalance, especially if you're looking at rare events like failures. So if you have 1,000 wells and then you're looking for ESP failures, maybe it fails in 10 wells and not in 990 wells. So you have to come up with some way of rebalancing, otherwise the results will be biased towards the non-failure case. Here is how you calculate the performance. So this comes from biostatistics. You look at the true positivity and the false positivity, and then you calculate these metrics. So as you go to perfect prediction, you're going basically from 0 to 1 along the true positive scale and then going across. So that gives you an AUC of 1. And in the other extreme, AUC equals 0, where you have perfect negative correlate, perfect inverse prediction. And in between, if you're on this line, then you have an AUC of 0.5, which means that you can't really distinguish between the two different classes. Other classification metrics, we create what's called an error matrix. And within the error matrix or this contingency table, we're just saying that, what's the 2x2 depiction of the predicted class versus the actual class. And based on the true positives or the true negatives or the false negatives or the false positives, you can calculate these quantities called sensitivity or recall, specificity, accuracy, precision, etc. And there is a composite score called the F1 score, which is the harmonic mean of the recall and the precision. And so oftentimes you'll see classification problems reduced to just reporting the F1 score. Now we will move on to some case studies and examples. So I have 3 case studies. The first is a reservoir or production problem. This is about the productivity of shale wells, described in this paper that appeared in SPE journal a few years ago. We have data from about 500 wells from the Wolfcamp formation in the Permian Basin in West Texas. The variables are listed here. In red, we have the response variables beginning with M12CO, which is the cumulative production over the first 12 months. Or we can take the maximum monthly production, or we can take the production divided by the length of the lateral. And we end up using the first one, which is the cum production of the first year as a response variable. The predictors are shown here in green, and these are related to the characteristics of the well. When was it completed? What was the TVD? What is the length of the lateral? And so on, versus the details on the completion. How many frac stages, total volume of fluid used to frac the well, the total proppant amount, and the proppant concentration. And so our goal is to fit M12CO as a function of these 12 predictors. We use multiple regression modeling methods. We also use model validation and variable importance. So we begin with the scatterplot matrix, and so this is where we have the response variable at the top, and then over here, we have some of the predictors: the completion year, the length of the lateral, the fluid, the proppant, the X and the Y locations, which is sort of a proxy for the geology, because we didn't have any information about the geology, given that this was a public data set. So what you can see from a visual examination of the scatterplot matrix, and this is what one would call descriptive analytics, is that there doesn't seem to be a very strong correlation between this response variable and these predictors, as you can see by the scatter nature of the responses here. Now, some of the variables seem to be correlated. For example, propellant and fluid volume and the length of the lateral, they all seem to be correlated. And that's what makes sense. We also see some correlation between surf X and surf Y, meaning that there's probably a ridge along which all of the wells were developed. And that's why we have this negative correlation. But we can use this to identify, oh, it looks like there is an outlier, and so whether this is just a human error and basically there's an additional zero where it shouldn't be the case, or this is a true outlier, that's what needs to be investigated as part of this first step. So this is exploratory data analysis, and then that's how we start looking at the data. This is a busy slide, but I'm showing a number of different things. First of all, we have multiple modeling techniques. So begin with the ordinary least squares, which is just your multivariate regression. And for me, that's always the baseline, because your machine learning black box model should never underperform the simplest modeling technique that should be possible, which in this case is the multivariate linear regression method. And then at the bottom, we have kriging, which is generalization of the geostatistical interpolation. In between, we have random forest, but the random forest turned out to be also similar to gradient boosting machine and support vector machine in terms of performance. So that is the only one that I'm showing here. In the right-hand column, we have the performance against the training data. So if you look at how the model performed with all of the data used to train the model, this is what you get. And obviously, it seems like kriging is doing a fantastic job, but that's by design, because by definition, kriging is a perfect interpolator. So if you give it any data, it'll always pass through the training points. But more important is what happens when you do the 10-fold cross-validation, meaning that you do 10, 90, 10 splits, and then you cycle through these 10 subsets, and then you assemble all the blind predictions and look at the correspondence between the actual QMOL versus the predicted QMOL. So you see a much higher degree of scatter compared to what you had here. And then that actually seems to be very similar to what you have for the random forest, meaning that if you wanted to go by the ability to predict for new data sets, the random forest is actually slightly better than the kriging model. But that is what you wouldn't have known just by looking at this column. So that's the major takeaway, is that always look at the performance for a blind, for an independent test set or the cross-validation test set to really assess the predictive accuracy of the model. Once again, a busy slide, but what we're doing here is we are using the R-square loss idea and utilizing the R-square loss value to rank different variables in their order of importance. So I show here ordinary least squares and support vector machine, random forest, gradient boosting machine, which basically have the same degree of overall R-square. But as you go through each of these methods, you see there is a lot of fluctuation, especially in the middle. And by averaging across the ranks, you come up with a better understanding of how these methods are robust or not. It's sort of like having multiple judges in a figure skating or a dance competition, whereas you're not going to be biased by the input of any one judge. And as you do the averaging across all the judges, you come up with some consensus estimate of the quality of what you're getting. And that's precisely what we're doing as we do the averaging across the ranks. You can also display that using these box plots. And so you say that, okay, this is important. Then you have another cluster, then you have another cluster, and then you have another cluster, so on. So that is why don't get too hung up on the difference between an average rank of 4.8 versus 5 versus 5.2. They're all the same. And so that's kind of the lesson here. Once you've built a model, you want to apply it for looking at what if scenarios for designing maybe the next well. So you could do the traditional one-off sensitivity analysis. So if you're looking for the relationship between M12CO and lat length, the length of the lateral, you can hold all predictors at their median values, and that gives you the red line. But really, that would not be realistic, because what you should do is you should control for correlation, meaning that if you're increasing the length of the lateral, your volume of fluid needed to frac the well also increases. Your volume of your amount of proppant needed to frac the well also increases. Maybe the number of frac stages also increases. So that's what gives you the blue line. So this is what's called conditional sensitivity analysis. And it's also another way of looking beyond the black box of nature of the model. We can take this regression problem, we can also convert it into a classification problem by saying that, okay, we're not just interested in the value of M12CO, but can we separate the top 25% of the wells, for example, or the top 10% from the bottom 25% or the bottom 10%. So in this case, we can apply a binary classification, and using the classification tree, we can come up with these decision rules that if the proppant value is less than this, and if the length of the lateral is less than this, we will be in the bottom 25% category. Whereas if the proppant value is greater than this, and the TVD is greater than this, and the length of the lateral is greater than this, we will be in the top 25% category. You can capture that using these confusion matrices, using these error matrices. You look for the correspondence between the bottom 25% and the top 25%, 62 out of 69. Top 25% versus top 25%, 73 out of 91. So with an overall accuracy rate of 70%, which is not bad at all in terms of getting a better insight on what are the good wells versus the bad wells, in addition to building a model that can give you the ability to predict the production of the well given the completion parameters. I'm going to skip this slide. Just talks about what happens if you combine the model predictions. You get some improvement over the individual predictions. The second case study is about the characterization of vaguelar zones. And these vaguelar zones are present in carbonate reservoirs. So they create hypermeability pathways. You identify them from cores or from image logs. An image log is where you lower a camera and basically you get a 360-degree view of the wellbore. And that is how you can identify where are the zones of high density vugs, where you have large vugs, where you have dolomitization, meaning that those are not high permeability zones. And so oftentimes you have a situation where cores have not been collected, the advanced logs have not been run, you only have the basic triple combo log. And so the challenge is, can vuggy zones be identified from the well log response alone? And we are going to use exploratory data analysis and machine learning to create classification rules as a way of building a data-driven model. Machine learning phase one is where we start by having our geologists create this binary indicator. 0 means no vug, 1 means vug, by looking at the image logs, by looking at the cores. And so you have the 0-1 trace. And we use that as a ground truth to train several models to detect vugs using the sensor log data, meaning the basic triple log data. And here you have the performance of a number of different models. And it turns out that the support vector machine has sort of a good performance. So that's what we select going forward for the next phase, where we are working with a data set of 10 wells. These are actual wells that were drilled in the Appalachian Basin in Ohio to dispose wastewater from the Marcellus shale fields from Pennsylvania. And so those wastewater trucks came to Ohio and they were basically injecting into these formations, particularly seeking out these Vagela zones, because those were zones with high injectivity. So in this second phase, we decided to do the hold one out kind of a validation process. So we would train the model with 9 wells, and then we would do the prediction on the held out well. And here is a listing of the correct identification rate going from about 60% to about 90% with an average of about 75%. So once again, this is very good performance because you are avoiding the additional task of collecting cores and collecting image logs. So what do you do as far as predictions are concerned? Well, you create this probability of VUGs shown here in the blue line. You convert that into a binary indicator. If the probability is less than 0.5, you say it's 0. If it is greater than 0.5, you say it is 1. And basically, we're looking for the correspondence between the actual zone of high VUG intensity versus what is predicted. And that seems like a good match here. And the same thing with respect to the second zone. This is the high VUG intensity zone, and this is the corresponding zone that was predicted. So good agreement between the two. We can map this in multiple wells. So we have the gamma ray, we have the neutron porosity, and we have the bulk density logs. And then we combine that to create the probability of the VUG, which is shown here. We can take the warm colors, meaning that there is a high probability of encountering Vagela zones, and we map them across this 3-well space. And we see that we have a high density of VUGs in the middle well. We have a lower density here in the left well, and we have very few VUGs in the right well. And then we sort of do a dynamic validation by looking at data from the dynamic pressure and rate information. So the injectivity in the left well was 5 barrels a minute. In the middle well was also about 5 barrels a minute, if not higher. And the right well was only about a barrel a minute, which confirms what our VUG prediction model is showing. The third case study is about the prediction and optimization of drilling rate of penetration. So the goal here is to fit a data-driven model to predict and optimize rate of penetration during drilling. The example is data from a vertical well in Texas, and these are the ROP measurements along the well. As you go down and as you encounter these different formations, the ROP keeps on decreasing as you would expect, but we have a lot of good data. And so basically we want to correlate that to selected features such as the weight on bit, the rotary speed of drilling, the rock strength, and the flow rate. So in terms of model fitting and validation, we started with the random forest model, which has a very good performance. The linear regression model does not work as well. And for one of the formations, which is the Tyler sandstone, we can show the comparison of the random forest and the linear prediction model. So the random forest clearly works quite well compared to the actual data. So the green versus the blue, whereas the red, which is the linear regression, is just off. And that is confirmed through these box plots of the errors. So clearly the error level of the random forest is much lower than the linear regression model. And for all other formations, the random forest is less than 10%, and that's kind of shown by this scatter plot. Then comes the question: how do we do an optimization in real time, near real time? So basically, we can take this data-driven model, and then we can explore the feature space for improved rate of penetration. By changing the weight on bit, the RPM on the flow, and we use the feature subspace in the vicinity of the depth of interest. And what we're trying to do is we're trying not to extrapolate, but basically expand the range of the training data. And that sort of tells us that by changing 3 features, we can increase the ROP by something like 24%. And so, you know, in a practical sense, what we would do is we would go and say that, okay, let's predict what's going to happen over the next 50 feet or 25 feet, and then run the model very quickly, and then get the results, and then use that in practice. Then as we are collecting data, that sort of goes as a feedback process into the model update and the model go ahead prediction. So that's how we can improve the performance and the cost savings. I have a number of examples. I will not go through these, but just to point to these papers, which, for example, show how you can apply classification and create these electrophases, and you can create the decision rules for these electrophases. In the second one, you know, how do you have good predictions in a small data set, even if the number of wells is only about 80 or so, because you have the right variables, which is a combination of geology and completion variables. And this is how you can make predictions in a way that makes sense, because if you go from 10 frac stages to 15 frac stages, you want to increase your proppant mass and fluid volume, and that is how you can get the best understanding of the predictions. This is an example of proxy modeling. So in proxy modeling, you're trying to capture the output of a reservoir simulator by creating these designs. So you can either have a classical statistics-based 3-point design, so like a low value, a medium value, and a high value. And once you run the model with those values, you create a response surface, or you can use some sort of a maximum latent hypercube sampling or a maximum entropy design, which has more granularity, and then you use that to generate the training runs, and then you fit it with quadratic and Kriging models, and you can evaluate the performance using cross-validation, and then you can say that, okay, now that I have this model, I can use it going forward. Here is an example of predictive maintenance. You know, first is identifying which are the incidences of failure, and then going through a cross-validation with 2 different models, and then that is how we come up with the conclusion that the red model is better than the blue model. And this is an interesting paper because it's about natural language processing and about the application of text mining. So you collect data, then you go through some statistical analysis, then you do principal components and clustering, and basically identify combination of conditions based on just looking at daily drilling data. So this is all text mining, and here is a combination of words and phrases that produces good outcomes versus bad outcomes. So let's recap what we have learned. First of all, problem formulation is important. The second lesson is that predictive modeling is nuanced because you have these black box models with lots of knobs that may lead to the existence of multiple competing models. Data quality quantity can compromise results. It's not always that lots of data meaning automatically good model fits. Unwrapping black box models is difficult, and this is where you have to go through different approaches like conditional sensitivity analysis or variable importance to understand what really is the underlying relationship. And communicating results can always be challenging, especially for people who are not well versed in the data analytics language. And then finally, text-based data sets are mostly untapped. So that is really an untapped frontier, and lots of possibilities exist there, especially in the oil and gas sector. So with that, I think we are just at about the break time. So once again, be happy to take any questions.
Yes, sir. We have a question. So
Sure.
I'll just read it out to you. So out of all those predictive methods, which one is the least dependent on the closeness of the starting set of the variable values to the solution set?
In these techniques, it's not like nonlinear optimization where you have to start with some initial guesses. So you just let the model go from. You just let the model take its own trajectory. And so the initial conditions are not as important here as they would be in traditional nonlinear optimization. So there is some robustness to the starting values.
Okay, sir. For more questions, you can put up your questions in the chat box.
Quick announcement. People are asking if they will be provided a certificate for participation. Yes, we will provide a certificate for participation, but for that, you will have to mark your attendance through a link you will send, for, Google Form link. And that will be shared anytime during the workshop in the chat box. Now, if you cannot see the chat box, please rejoin the meeting, okay? Yeah, that's all.
So I see a couple of raised hands.
Hi, good day. I have a question.
Yeah.
I want to take it back to the top a little. I've had this question in my mind for a while, and it's a very interesting and great topic that your session that you guys are having that is starting me to ask the question. With respect to supervised learning, is it safe to say that when you're calibrating an equipment, for example, like one of your downhole logging tool, in calibrating your downhole logging tool, there's procedures you'll follow in terms of calibration standards that will have artificial defects that you're basically telling the equipment what to look for when you put the hole down, when you put the tool down in the hole. Is it safe to compare that being calibration as supervised learning?
In some sense, yes. In some sense, yes, because you have a target value that you're trying to get, and you are adjusting some coefficients in how the actual measurements are then translated into an attribute that is of interest. So if you're measuring the current and the current becomes translated into, let's say, something like the gamma ray value, then that's what you're going through. So it is a process of supervised learning, but I would say that that's a very limited application of supervised learning, because what we want to do is, once you have the logs, so you have the gamma ray log, you have the neutron porosity, you have the bulk density, then you want to combine them and say that if I had some core-derived permeability at these depths, can I come up with the relationship between permeability and these log attributes? So that would be a more conventional application of supervised learning. But supervision is really when you have a target that you're trying to match. So that's the broad sense of supervised learning. Somebody else has the hand raised, Raj Kiran.
Yeah, so I will just ask you another question. So, like, I have been working in this field for almost 2-3 years. So one of the main challenges is, as you rightly pointed out, the problem formulation. So do you have any suggestion that how we can develop the problem formulation skill? Because that is the biggest challenge which we see. Like, if we give some students some project, either they can look at some papers and try to do something related to that, but how they can come up with the problem, like, and the approach, because it's very difficult to take a problem until and unless you do the whole thing. You don't know that whether that problem will be solved through that machine learning or something like based on this data science modeling. So do you have any suggestion regarding that, how we can develop the problem formulation skill?
Yeah, that's a very good question, and I will come back to this also after the break when everybody is here towards the end. But let me address that now. In my mind, that is sort of absolutely the most important step. And in a way, I see a lot of people sort of desperately trying to apply machine learning to a problem, to any problem, without thinking too much about the problem. So my recommendation always has been, ignore the machine learning part. So first sit down and think about what is it that you're trying to answer? What is the question that is being posed? And why is it that you're unable to answer the question as it is posed? Is it because your computational model does not exist? Is it because you do not have the data to run your computational model, your physics-based model? Is it because the computational model takes too much time? Or are you just looking for an alternative representation of the input-output relationship? So in any case, you should be able to articulate the question before you even think about machine learning. Now, when you articulate the problem, what you need to do is you need to ask the question that, okay, I want to know how my production rate, for example, depends on the completion and the geologic variables in a new field. And to that end, you must also say, okay, what specifically are the causal variables? What are the geologic variables that I need? What are the completion variables that I need? And it could be that, you only have a subset of the information that is needed. Sometimes you have soft information rather than hard information, but all of that needs to be assembled in terms of the problem statement. And then, and then you can go from there.
Thank you.
So we are, okay, I am going to take a short break and I'll come back in about 6 minutes. So which will be 10 past, what, 8? Your time?
It's 8:05 here.
Yeah, okay. So let's come back at 10 past.
Thank you.
So one announcement to all of you. We will be sharing a Google form for marking your attendance so that you guys can receive participation certificate. So be active and check the chat box.
We haven't sent it yet. So a reminder for everyone here, if you're not able to access the chat box, you might leave the meeting and join. You'll be able to see the chat box and the link will be circulated in the chat box anytime.
All right. It is 10 past the hour, so let's resume our discussions. So in this last module of today's presentation, I'm going to do a little software demonstration. So the software that I'm going to be using is called R, which is a freely available language and environment for statistical computing and graphics. It provides a wide variety of statistical and graphical techniques for linear and nonlinear modeling, statistical testing, time series analysis, classification, clustering, machine learning, etc. And this is the link to download this freely available software. Then we have Rattle, which is a popular graphical user interface for data mining using R. It represents statistical and visual summarization of data, data transformations, supervised and unsupervised machine learning models, and You can also score new data sets for deployment into production. So basically it works with R running in the background. And here is how you can download the Rattle program. The two problems I'm going to show you, one is a regression problem. So the data set is Salt Creek Regress. And I will share with you this, this data set together with my slides so that you can play with it on your own time. We have 5 well logs as inputs, the log 10 of LLD, gamma ray, neutron porosity, bulk density, and photoelectric logs. We can use permeability as the output. We'll do exploratory data analysis. We'll do some modeling with linear methods, tree, random forest, and neural nets. Look at model validation and also, to some extent, variable importance. The second problem is a classification problem using sort of a variant of the first data set. So we have essentially the same data, and the permeability values have been classified as high or low, depending upon whether they're in the top 25% or the bottom 25%. And so once again, a number of different modeling techniques, validation, variable importance. Sorry, not wrap up comments yet. I am going to start. So I'll start R. And once you start R, you go to your R console and then you type in library Rattle. It loads Rattle. And then when you type in Rattle, it takes you to the Rattle interface. Now, I just wanted to go through what Rattle can do and what is the menu structure. So you have a number of these actions, but the most important one is execute. You sort of have to use the execute button after every command. So that's something to keep in mind. And then you have these different analysis related tabs: data, explore, test, transform, cluster, etc. So in the data tab, you have these different formats in which you can read the file. Typically, you want to read the file as a CSV file, so comma separated variable file from any spreadsheet. So that's what we will do. So we're going to read the Salt Creek Regress data. And then I hit execute. So it'll tell me that I have read a data set which has these variables, and it automatically sort of tries to identify which of them are the inputs and which of them are the targets, which can be ignored, and so on. And how is the data going to be partitioned between the training set, the validation test set, and the test set. For the time being, we're going to ignore that. And we will make, ignore this class variable. And so we just have these 5 inputs: gamma ray, log 10 LLD, bulk density, neutron porosity, the photoelectric log, and then log of permeability. So all of these as inputs, just so that we can, go through some basic visualization. So I have executed that, and then I go to explore. So in the summary, I have all these options. So I'll show you what they do. So in summary, you will basically get some output about the minimum, the first quartile, median, the mean, etc., for each of the variables. Then if you go to describe, you will get a little bit more information with respect to the number of observations, how many missing values, how many distinct values, what's the mean, what's the geometric mean, what are the different percentiles going from the 0.05 to the 0.95. Oops, sorry. And then what are the 5 lowest values? What are the 5 highest values? So in the basic functionality, it gives you more information about things like the mean, the median, the upper confidence and the lower confidence limits for the mean, and the skewness and the kurtosis and so on, which basically have to do with the degree of asymmetry in the data. You can do a number of different statistical tests, which are not relevant to what we're doing here. You can do transformation. For example, if you have a variable that you want to change from the actual value to the natural log, you can do that. You can recode something by saying that something is a categorical variable or a numeric variable. You can clean up by saying delete all observations with missing values and so on. So it's a good functionality for manipulating different data. We go back to the Explore tab, and then we look at distributions. So it gives us a number of different options. So let me just go with the box plot first. So I just check the box plot option. I have to use this Cairo graphics device setting. What it does is otherwise it would just create a number of different plots and sort of keep on overwriting the plots. In this setting, it just allows all the plots to be individual. So if I hit execute, it'll give me all these box plots. So from the box plots, I get some idea as to whether the distributions are symmetric, what are the outliers, etc. Come on. And then instead of the box plot, let me look at the histograms. So with the histograms, you can once again get a better idea of the degree of asymmetry in the distribution and whether there are outliers. For example, here it seems like there could be some outliers. Here there could be perhaps some outliers, and we already have 2 symmetric distributions. This log 10 LLD and log of kg. That's because maybe they have been already log transformed. These 2 variables have different kinds of asymmetry, and so one possibility might be to look at whether a 0-1 transformation or a rank transformation or a log transformation can make it symmetric. Let's look at correlations, and we can look at both Pearson and we can look at Spearman. The Kendall option is basically Spearman, but that's to be used if there are ties, meaning that there are 2 values with 2 samples with the same values, which means that there is a tie in the ranks. But let's just go with the Spearman one for the time being. And so I have 2 things. I have the correlation matrix, and then from the matrix, you can look for actual values, whereas you can also look at the bubble plot and then see which variables are correlated with which variables. And also, if you're interested in log of kg, it seems like it's mostly dependent on rho B and phi, and has a very small dependence on PEF. Then we go to the modeling part. And in the modeling part, before we do that, we have to make log of kg as the target. And we can do an 80-20 partition. What that means is we're training on 80% of the data, we're testing on 20% of the data. So we do the execute. And we go to model. And we start with tree. And there are a lot of these options. And once you hover over each of these options, it'll basically tell you what is that user adjustable parameter and what is the default value. So here is the same thing. Now, this is really the most important adjustable parameter in terms of complexity. So you can make the more complexity value very 0, and then the tree will be quite large, and as you adjust it, you come up with some sort of a trade-off between the complexity of the model and then the accuracy. So if I hit execute, I get the decision tree, and then I get this table, which, oops. So I have to look for the sum of these two values, and that's what it says here, is that you will look for the number of splits where the sum of the X error, the cross-validation error, and X STD is minimum. So that's kind of the optimal split here, and it seems like that would be something like 0.77 plus 0.066. So maybe, value of 0.07 is the optimal. And we have, yeah. But, and then you have these decision rules, and you can go through the decision rules and then figure out what it's telling you. You can also look at the tree, and basically this is the tree that's been created with all of these terminal nodes, and so you've discretized permeability into these ranges, and that's what you're getting in terms of the model. Okay, so that's how you build the tree. The next model is going to be the random forest model. So once again, the two adjustable parameters are the number of trees and then the number of variables. And so if I hit execute, it builds the tree. It gives me what percentage of the variance has been explained. It calculates the variable importance. So this is an interesting feature. It basically says that if I take bulk density rho B, and if I randomly shuffle the values and then predict my performance, I'm going to get a 45% increase in the mean squared error, which means that it has a significant effect on the variable. Whereas if I took my log 10 LLD and if I randomly shuffle those values, I will only get a 10% increase in MSE. So obviously, rho B is going to be more important than log 10 LLD. This is what you also get by clicking the importance button, and then when you look at these bar graphs, so percent of increase in MSE, you will get an idea as to which is important and which is not. We can look at the errors, and that is to show, do we have too large a model? Do we have too many trees in the random forest? And basically what we can see is that from about 160 or so, the performance of the model seems quite stable. And so what we can do is we can change this. So keep an eye on this variance explained, which is 40.94. And let me change that to 160 and execute the model. So that is 41.05. Actually, the performance improved just a little bit, even though in this statistical sense, these quantities are about the same. Okay, so that was the forest model. Then we can go to the linear model, and I use the generalized option here. So I hit execute. So we have the same table that we saw in one of my earlier slides. This is the one slide cheat sheet for regression. And why do I have the linear model? Because that is really the baseline. I mean, your performance should never fall below the performance of a linear model if you're evaluating a black box approach. So here we have the estimates, the standard errors, the t values, and the p values. So in most cases, we can see that PEF, in most cases, the p values are actually quite small, with one exception, which is the PEF, and that seems quite large. And we can keep note of this AIC, and we can drop PEF from the model, and then we can see what happens to the AIC. Yeah, maybe I'll just go ahead and do that. So if I ignore this, and then I execute the model, and then I go back to linear, generalized, and execute. So now we see that that AIC is pretty much the same. It was 1168.5 or something. Now it's gone down a little bit, but we have dropped one variable, which means that we have not really suffered anything from a statistical standpoint by going through this process. So this is with relation to my slide, how many variables are needed in the regression model using the AIC. So that's basically what I went through right now. I'm going to put that back in the mix. And now we go to model, linear, generalized, execute. So this is 1168.6, whereas in the previous case we had 1168.4, which means that the 4 variable model is actually better than the 5 variable model. Then we go to neural net, and here the thing to point out is that in the implementation that we have in Rattle, there is only one hidden layer that is allowed, as opposed to multiple hidden layers. But what we have control over is the number of hidden layer nodes. And so we can start with 10 hidden layer nodes. And if I hit execute, you will see that it has 76 weights. Meaning these connections between the inputs and the outputs, and gives us a sum of squares, a residual of 592. So what if I had 3? So that is 600, which means that I haven't degraded the performance too much. If I do 7, then that's 562, meaning that it's actually doing better than the 10 layer model, and that too with a smaller number of weights, 55 as opposed to 76. So then we can go to the evaluate tab, and we can go to predicted versus observed. And we can look at, oh, I probably need to build my tree models again. All right, I can build my forest model. I can build my tree model. And now when I go to evaluate, it tells me that I have the tree model, the forest model, the linear model, and the neural net model. But I'm going to look at each one of them separately. So here is the performance with respect to the training data set with a pseudo R-square of 0.31 for random forest. It has a pseudo R-square of 0.42 for the linear model, pseudo R-square of 0.31. And neural net is a pseudo R-square of 0.29. So this is how you can evaluate the model, and you can also score them and write the output to a CSV file for all of these models. So when you hit execute, so that's where it's going to put the data. And then if I go to my desktop, when I open this file, you will see that it starts with the actual value and then the predictions from each of these values. So you really have a nice way of capturing the data that goes behind the plots, which I was showing you. So these are the plots that we did, and these were the prediction with respect to the test data, and that is what we are capturing here. And because so it should have 80 data points because we had 400 to begin with, and 20% was a test data set. So that's what we have here. All right. So let me see what time we have here. 11:01. Okay. Now let's go to the classify data. And I will overwrite the previous model. And so I'm going to ignore log of kg and then keep class as the target, because what happened was that the log of kg values are directly utilized to calculate the class value. So if I use log of kg as a predictor, then everything will be perfectly predicted. I don't want that. So I execute that, and the data set is still the same. So not much to do with respect to the Explorer, but let's just see one thing here. Okay, so I can create these scatter plots where things are organized by class, and let's see what we get. So you can get these conditional distributions, and it says that I've taken the log of kg and I've created these two classes, so that's why they're very cleanly separated. If I look at some of the other variables, which means that, if I'm looking for the individual sub-distributions corresponding to classes A and B, this variable does not seem to be an important one, whereas with NFI and ROBI, there's clearly quite a bit of separation. PEF is sort of acting like log10 LLD, whereas gamma ray is also showing some separation between the two classes. So once again, this is descriptive analytics that helps you understand, if I have two classes, what is the underlying distributions and whether those distributions can be separated or not. All right, so now we go to model. And here I can build a tree-based model. Same thing, you see the outputs. I can build a random forest model. We can look at the errors. And we see that because there are two classes, A and B, so this is what we have for class A, this is what we have for class B. The errors are higher than we had before. We can build an adaptive boost model, which is where we are building a sequence of models and then we're combining them. And then we can build an SVM model, support vector machine model. We can build a neural net model. So the reason why I'm sort of flying through all of these model building processes is not really to show you how each model building process works. It's to sort of give you a very quick overview of the functionality and the ease with which you can call these models. So obviously you need to understand what is involved in pressing that button. So when I press that neural net button with 7 hidden layer nodes, I need to be able to understand what is the output here and how I can utilize my adjustable parameter value to really optimize the model. Then we go to model evaluation, and here we're looking at error matrix, and we can look at 1, 2, 3, 4, 5, and we can look at the performance with respect to the training data. So for the decision tree model, the overall error is 10%. For the extreme boost model, the overall error is 7%. For the random forest model, the overall error is 0, which means with the training data, it's doing very well. With the neural net model, it's 13%. With SVM, it's 14%. If I go back to data and then if I partition it into an 80-20 just to see what happens when I do some blind testing. So I hit execute. Then I would go back to model and then I would train each one of them separately. I would do the boost. I would do SVM. I would do neural net, and then I would do the evaluation with respect to error matrix. Now I'm doing the evaluation with the testing. So now you see that for the decision tree model, the overall error with the test data is 5%. With the extreme boost model is 12.5%. With the random forest model is 20%. With the SVM model is 22.5%. With the neural net model is 20%. So that is how you can look at the individual model performance. Now let's look at the training data. Let's do a score, and we can put it in the CSV file. Oh, okay. For some reason, it's not going to be doing that. Okay, all right, that's not a problem. But you know, once again, this is not introducing you to the full utilization of the capabilities of R and Rattle. Just to show you that, you know, you have this tool, which is an open source software, and it allows you a programming free environment for getting into data analytics and machine learning. So to me, you know, as a teaching tool, this is very, very useful because you don't have to worry about syntax, whether it is writing R scripts or whether it is writing Python scripts. But this is how you get introduced to different concepts. And then once you've done that, you can write your own algorithms and you can write your own scripts to do the analysis. The other nice thing about this is that it creates a log file, because basically with every click it is creating, it is generating some R code, and this is the R code that you would actually write on your own if you wanted to do this using the R console as opposed to Rattle. So every time you click a button, you are generating this code. And let's see, the last thing that we did was that yeah, so you know, you're generating the plot, which means that you're activating these commands. Then you're building the decision tree model. So this is what the decision tree model command really looks like. And obviously you are not writing these 6 lines of code. You're just creating this workflow, which is the effect of what happens when you press the button. A couple of things I wanted to show you here as well. And that had to do with the Explore. And so we can do the principal component analysis. Typically, we use the SVD format, which is the singular value decomposition of the correlation matrix by doing the centering and the scaling of the raw data. And so if you hit execute, you're going to get the plots that I showed you earlier. This is for the same Salt Creek data. And so here are the eigenvalues corresponding to the first 5 principal components, meaning that the first 2 account for something like 3/4 of the total variance, and the first 3 account for 90% of the total variance. In terms of the dependence of the individual variables with respect to the principal components, PC1 is going to be dependent on NP, log 10 LLD, and rho B. PC2, which is on this axis, is going to be dependent on gamma ray and PEF. So essentially what we saw in the slides. We can also do a cluster analysis. And let's see, we do a k-means with 5 clusters. And if we do a discriminant plot, we will get something that sort of looks similar to what we had in the slides, but sometimes there is a little bit of a randomization with respect to the data, so that's why this looks a little different. So that was sort of a very quick overview of the R Rattle software. And because you have access to this video, you can actually stop the video and then replay what I've done. So think of this as the equivalent of a YouTube video for learning a little bit about R and Rattle. Now, there are lots of other videos that you can find that will help you learn about this software if you want to use it. There is also a book written by Graham Williams, who's a developer of Rattle, on how to use this for data mining. And so those are good resources. I mean, it does not have all of the functionalities and all of the features that you want, but it has a large number of features, at least as a good teaching tool. With that, I am going to stop for a few minutes to see if anybody has any questions before I go to the wrap up.
Yes, sir, we have quite a lot of questions. So I'll just read them out for you.
Sure.
So the first question is learning R and R based applications for data analytics sufficient, or there are some aspects in Python based applications not in R?
To my knowledge, the functionality of both Python and R libraries are comparable. It could be that some Python packages, particularly now, are a little bit more elaborate than you have in R. I mean, traditionally, R has been the software of choice for people who come from a statistics background, and Python has been the software of choice for people who come from either a computer science or a computer science or an engineering background. But Python is becoming more and more common in terms of utilization. And I would say that there is really no distinction between the two, with the only caveat that, to my knowledge, there is nothing like Rattle that is a purely graphical user interface for learning, for running Python scripts.
Okay, sir. So the next question is it possible for this application solving and determining the hypothesis?
Sorry, possible for the application to be what?
So the question says, is it possible for this application solving and determining the hypothesis? I don't think the language is correct.
Yeah.
Might as well rephrase your question.
Yeah. So let's go to the next one while this is being rephrased.
So the next question is, R-based application appears to be more user-friendly. Is learning R and R-based applications? So I think it was the same question. R and R-based applications for data analytics sufficient? I think it's the same question.
Yeah.
Somebody sent it again.
Yeah.
Okay. So yes, and there's one more question. Can you please show how you define the objective function and adjustable parameters in the regression model?
So in the linear regression model, the objective function, okay, I can't do linear regression here because it's a classification problem. So if I go back to my regression data set, so the target is log of kg. I'm going to ignore this. Let me convey the partition. So I execute this. So my my target is log of kg. And then when I do the linear model using generalized, so here it says that I want to fit a multivariate linear regression model. Log of kg, when it says tilde, it means that it's a function of these variables. And when it's a function of these variables, so you have alpha plus beta 1 times gamma ray plus beta 2 times this variable plus beta 3 times this plus beta 4 times this plus beta 5 times this. So you have alpha and then the 5 betas, and that is the that is how the objective function is specified that you're minimizing the deviation between the prediction from this model and what you actually observed. So it's a least squares minimization function in the typical linear regression format. And you're estimating these parameters alpha and the 5 betas. So these are the mean values and these are the standard errors. And that is how you can look at the p values and the t values.
Okay, thank you, sir. Got it.
Sorry, you're muted, Ishika.
Oh, sorry, sir, that was my fault. And I think we're done with the questions now. We don't have any more questions in the chat box. And if you have any other questions, you can just raise your hands and ask yourself.
All right, excellent. Thank you all for being patient throughout the day. A lot to do on a Saturday evening, but we are almost there. Just a few final comments.
Yes. So with this, we come to an end of this insightful event. Dr. Srikanta Mishra, we're really thankful to you for sharing your bit of knowledge. And
wait, I'm not done yet.
Okay, sir.
Ishika, I'm not done yet. I have maybe about 5-7 more minutes to talk about. Okay.
Yes, sir.
Okay.
Yeah, so first, here is a list of books that you can pick up. I hope the library has these books, but just to give you a flavor for petroleum data analytics related resources, I've already talked about the book that Akhil and I have written, and then you have Data-Driven Reservoir Modeling by Shahab Muageg, who's a petroleum engineering professor at West Virginia University. There's another book, a recent one by Srikanta Mishra and some of his students. He's a professor of petroleum engineering at Texas A&M, specializing in formation evaluation. And his book actually has a number of Python scripts that can be used for essentially doing what I showed using R. Keith Holdaway is with SAS, which is a big statistical software package. And so his book deals with the application demonstrating the capabilities of SAS. Trevor Hasty and colleagues from Stanford have written this book, The Elements of Statistical Learning, Data Mining, Inference, and Prediction, which is one of the best books out there on the theory behind the algorithms that we talked about. And then Kuhn and Johnson have a book, Applied Predictive Modeling, which is about the implementation of those methods within R in a package called Carrot. Now, in terms of software resources, in the companion site of our book, which is given by this URL, we have a number of different software packages and scripts. So for non-parametric regression, for multivariate analysis, for experimental design, along with R scripts for machine learning and other example data sets. We've talked about R. At the same time, Python is a very commonly used programming language with built-in libraries. There is Weka, which is the implementation of machine learning software using Java. Very nice user interface. Once again, open source, developed by the University of Waikato in New Zealand. And then you have a number of commercial packages, including the good old MATLAB, and then the more statistical software such as SAS and SPSS. Basically, what I like to promote in my lectures and presentations is not just focusing on the machine learning part, but the entire suite of techniques that is useful for data-driven modeling, beginning with exploratory data analysis and understanding of regression and multivariate analysis. Then, experimental design for creating proxy models using machine learning. And then the application typically is for uncertainty quantification or for history matching. But Monte Carlo simulation and uncertainty quantification also requires some foundational understanding with respect to the basics, and that's what we like to promote. In fact, in our book, we have systematically laid out things along this pathway, and that is sort of the mindset that we like to promote. So the recommended workflow for a data-driven modeling exercise begins with framing the problem, checking the data, and then selecting the causal variables, because that is where you either make or break the project. If you don't have the right causal variables, you're not going to get a good representative model. And then you pick the software, you choose the modeling technique or techniques, validate the model, and then understand and communicate the results. So in terms of some of the common challenges for the acceptance of machine learning models, here are a few. And also in a recent paper that was published in the March issue of the Journal of Petroleum Technology, we tried to take a holistic look at the state of machine learning for petroleum engineering applications. And basically we said, building robust data-driven models, are we there yet? And we identified these challenges for why machine learning has not received as widespread acceptance as one would like to think. And some of these are listed here. Our machine learning models are not very good. If I don't understand the model, how can I believe it? We are still waiting for the aha moment. My staff need to learn data science, but how? So the first question is about poor model quality. So somehow there is a perception that when you apply machine learning, you should get an R-square which is close to 1, because it seems like that's what Amazon, Netflix, etc. are getting. But that's really not the case. And so consumer marketing ML AI models are not necessarily highly accurate. And all of you have actually seen this in practice. And every time Amazon recommends a set of books or Netflix recommends a set of movies, you know that some of it is just garbage. And that's where we need to manage expectations with respect to the quality of fit of subsurface models. And we need to focus on the added value from machine learning models and the complementary role that they play in conjunction with physics-based models such as reservoir simulators or other analytical techniques such as well-test analysis software. In terms of lack of understanding, what we need to do is do a number of different things, such as articulating the adequacy of predictors. So if we can convince the decision maker that we have included all of the relevant variables, then they are liable to have more confidence in the model predictions. We need to demonstrate that the model predictions are robust. It's not just that we're able to get good fits to the training data, but we can also provide reasonable fits in blind testing to independent data sets. And that is one of the key components. And the other key component is to say that we need to understand the inner workings of the model in terms of the most important variables that affect the input-output relationship. So the opportunity to use creative visualizations to explain what the model is saying through things like conditional sensitivity analysis and other plots that sort of slice and dice through the results can help in making the model more accepted and the decision maker more confident with respect to what the model can or cannot do. The aha moment part comes when people are always expecting new insights. And this is where the expectation management also comes in, because we really need to recognize that the machine learning model may or may not produce new insights, but at least it provides an alternative quantitative input-output relationship that we did not have before, that is easy to implement and that is quick to run. And so these models can be useful when the physics-based model is slow, when it is data intensive, or when it is immature. Learning data science is one of those important questions, because everybody is interested in sort of transforming himself or herself into a data scientist. But what we need to do is sort of recognize that as citizen data scientists, we need some significant informal self-learning, especially about the foundations. And that means that we need some formal knowledge of conventional data analysis, Python, R programming, and machine learning concepts beyond watching a few YouTube videos or downloading some software from GitHub. A number of common questions that I have been asked during my lectures and short courses is, which software should I use? It once again depends on your objectives. If you want to do visualization only and focus on descriptive analytics, you can use things like Spotfire and Tableau. If you want to use light and easy statistics tools, then Excel and JUMP and SPSS and Minitab might be what you need. For commercial statistics software, SAS, MATLAB, Stata would be the options. And if you're only interested in open source packages, then either it's R, Rattle, or Python. Do I need machine learning? You know, that's a more fundamental question rather than assuming that machine learning is needed for each and every problem. So let's take the first case where, you know, once again, we're trying to predict minimum miscibility pressure from the underlying variables like temperature and the composition of the crude oil. So we have two models here, a simple linear multivariate model, which gives us an R square of 0.91, and a random forest model, which gives us an R square of 0.95. With the linear model, we know exactly how the variables are interacting. With the random forest model, we have no such clue. The second case is where we're trying to predict permeability from well-log attributes. With a linear model, we have a pseudo R square of 0.35. With a random forest model, we have a pseudo R square of 0.88. So in the first case, I would argue that we don't need to go beyond the linear model because it has transparency, it has acceptable accuracy. Whereas in the second case, we probably need to go ahead and do the machine learning based model building, because that is clearly quite a bit superior in performance compared to the linear model. Question 3, which technique works best? You know, we have this plethora of machine learning techniques, beginning with individual decision trees, the random forest, gradient boosting machine, support vector regression, kriging, neural nets, etc., etc. So what we have found and what others have found is that there is no single technique that is consistently the best performer across all problems. Not only that, we see that often multiple competing models have equally good fits in terms of the R square or the RMSE. So this is where our recommendation is to aggregate models, is to combine models, is to build an ensemble model prediction so that we can get robust understanding and predictions. And basically, we want to pick forest over trees. Just to demonstrate the power of ensemble modeling, let's take a case where we are predicting the production rate from 4 wells, P1 through P4, using the injection rate at 5 surrounding wells. So it's a water flooding problem. We have the water injection rates, and we're trying to predict the oil production rates. The first 66 months of the data I used to train the model, and then the last 33 months I used to test the model. So the performance of the training versus the test set with SVR, it's 0.99 versus 0.61. With random forest, it's 0.985 versus 0.91. With neural nets, it's 0.99 versus 0.944. And if you average all of the models, then you see that the training R square is once again 0.986. The test R square is 0.93, meaning that the ensemble actually gives you more robust predictions, even though you don't know which of the models will do best if you change something. And here is the important recommendation that one should always have a minimum of 3 models. One is a baseline regression model, a linear regression model, and then at least one tree-based model like either a random forest or a gradient boosting machine or both. and at least one non-tree based model, such as a support vector machine and a neural network model. So then, depending upon the performance, you can either select the best performing one, or you can select multiple ones and then aggregate their predictions. How much data do I need? It's not quantity, it's really quality. In this example, we had data from 81 wells for an unconventional shale well performance prediction. But as you can see, the distinction between the test and the train and the validation sets is not quite significant. That's because robust models can be built with small data sets if all relevant causal variables are included in the model. So in this case, we had variables describing the geology, we had variables describing the completion parameters. So that adequacy with respect to predictors was completely preserved. In the other case, we have a larger number of data sets going up to something like 3,000 wells. But we are building a model using simply the completion parameters and the well information, and clearly the R square of 0.27 leads us to the conclusion that large data sets can also produce poor results if key causal variables are not included in the model. So once again, it's quality, it's not quantity. How do I learn data science? So a citizen data scientist or an analyst is one who learns from the data. You have some basic skills, which are the domain knowledge in petroleum engineering. You need to pick up some new skills in statistics, machine learning, and programming. And so the core data science competency, so this is what a data scientist would learn as part of a data science undergraduate or a master's program. How to collect, prepare, and explore data, how to store and retrieve data, how to do computations with data, how to apply machine learning, and how to do visualizations. And really what we're looking at is the intersection between the computer science side of things, the math and statistics, and the domain expertise. So if you take a petroleum engineer and then you add that computer science degrees, you can produce a software developer. If you take the petroleum engineer and then you combine that with math and statistics expertise, that produces a data scientist. If you produce a computer science person and combine that with math and statistics, that becomes an advanced computer scientist, whereas the confluence of all three produces a petroleum data scientist. So looking ahead, we see that there is a growing trend towards the use of statistical and machine learning techniques for oil and gas applications. The goal is to mine big data and develop data-driven insights to improve reservoir description and performance prediction. There are broader applications in a number of different areas: digitalization, in real-time analytics, and predictive maintenance. But petroleum engineers and geoscientists, the so-called petrotechs, need to develop a better understanding of the full repertoire of available techniques and the potential, and not just become people who know how to push the button. Because if you do that, you are just a technician, and you need to understand the basics so that you can collaborate with data scientists and take full advantage of this exciting and powerful new technology. And at the same time, data scientists need to educate themselves, or need to be educated on the problem domain to propose and apply appropriate techniques. I'd like to end with this so-called Gartner hype trajectory. With every new technology, you move from a trigger, that is when the innovation has been identified, and very quickly it leads to a peak of inflated expectations with the idea that, okay, now I can solve all of my problems. And gradually that leads to a trough of disillusionment, where you realize that the early expectations were too inflated, and you may not be able to realize all of that. And as you acquire more case studies, then you go through the slope of enlightenment to reach a plateau of productivity, which is somewhere below the peak of inflated expectations. I would say that in terms of where machine learning is for oil and gas applications, we're probably slightly behind this peak of inflated expectations, and maybe slightly ahead of the peak of inflated expectations. There is the danger that we might just get mired in this trough. But that is going to happen if the expectations are not managed. If people who don't understand the technology rapidly jump in and then start using it, and that leads to undesirable outcomes. So with that, I just want to share with you this last slide, my final thoughts. Beware the hype and manage expectations as you go out into the world, as you apply data analytics in your day-to-day work or in your research. Just have a good understanding of what realistically can be expected, and so you learn how to manage the expectations and cut through the hype that is widely prevalent. The second lesson is that the machine learning part comes after posing the problem. Spend enough time to articulate the problem, to identify the causal variables, and to satisfy yourself that you have a situation where you cannot answer the question of interest using conventional techniques. And then whatever you do, don't forget the physics, because the physics always comes in through the identification of the causal variables. Physics can also come in through the expression of constraints into the machine learning framework. And this is the so-called physics-informed neural network or physics-informed machine learning that is becoming a new thing. So all in all, we have an exciting new technology, but it needs to be applied with understanding, with caution, and with good judgment. So with that, I want to thank you for your attention, for this opportunity to share my morning and your evening on this quick journey through machine learning and what it can do for petroleum engineers. I hope this has been a useful exercise. It's a great pleasure to give something back to my alma mater, and I'm delighted that I had the opportunity. So yeah, be happy to take any questions before we conclude.
Okay, if we have any more questions, you can just raise your hand and ask your question yourself. And also, sir, I'm really sorry for interrupting you in the middle of the illustration. Pardon me. I think there aren't any questions, so Arslan, go ahead.
So with this, we come to an end of this insightful session. Dr. Srikanta Mishra, we are really thankful to you for sharing your bit of knowledge and experience with us. It is for sure that our horizons have been broadened. And thank you so much for sparing this time for this informative workshop. It has been a deeply insightful experience for all of us this evening. So guys, stay connected for more such workshops and sessions, and thank you for your patience.
Thank you, sir.
Also, people who were worried about the thank you, sir. Also, people who were worried about the materials and the recording, it will be uploaded on the official YouTube page of SPE IIT. You can refer to it anytime you want, and also the slides will be shared.
Yeah, so what I will do is I will send these slides and the data sets that I use to Professor Kumar, and then he can share it with the people in the student chapter. If you have further questions, here is my email, and feel free to write to me. And Professor Kumar, if you have any other questions regarding putting together a course on data analytics, feel free to reach out to me. Be happy to help.
Thank you very much.
All right. With that, good night.
Yeah.
And
Yes, sir.
all right, good night.